This video is on differentiation using the limit of the difference quotient. And in the previous lesson we talked about the difference quotient. We'll refresh our memory here. So for this definition, all right, the slope of the tangent line. Now when I say slope of the tangent line, remember a tangent line only intersects the graph once, right? So the slope of the line intersects the graph once at a point. To f of x is given by, and we talked about this limit. We didn't actually do anything with it yet, but so it's the limit as h approaches 0 of the difference quotient, which is the f of x plus h minus f of x all over h. Now, we showed in the last lesson how we got this from slope formula. This is also called the instantaneous rate of change. Alright, so instantaneous rate of change at a point x. So in the past we talked about average rate of change. Average rate of change, we use slope formula between 2 points. This is the slope at a single point for the tangent line. So this is the instantaneous rate of change. So it's the slope right at that exact x value. We also call this the derivative. Alright, so in calculus we're going to use this a lot. So for our definition here, the derivative of a function y equals f of x is the function f prime of x. You see this little dash up here. The way we read this, alright, just to make sure you understand, is we're reading this as f prime of x. So you see that one little dash there, it's f prime. Sometimes you'll see 2 dashes, that's f double prime. That'll be the second derivative. We'll talk about that later. But have to understand that's f prime of x. And it's given by really what we just talked about. The derivative is the slope of the tangent line at a point. So it's f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Right, so that's what it would be, provided that the limit exists. And if it doesn't exist, right, so if it doesn't exist, then, the derivative doesn't exist there. If f prime of x exists, at a point x, then we say f of x is differentiable at x. So you hear the derivative, right? That means we're using this limit of the difference quotient for now. Later on, we'll learn some shortcut rules of finding the derivative. just to make it easier to work with. But you know, this is where the derivative comes from. It's the limit of the difference quotient. If you hear differentiate, that means take the derivative. It says find f prime of x, that means take the derivative. It says find instantaneous rate of change, that means take the derivative. If it says average rate of change, that means you're finding the slope between 2 points, which is different. So let's take a look at an example using this. So we'll say for this example, for f of x equals x squared plus 2x plus 1, first thing we'll say is find f prime of x. And we're going to do this by using the limit of the difference quotient. So let's make sure we refresh what we just talked about, right? So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And like I said, there are shortcut rules to this, but if for now we're going to use the limit of the difference quotient. If I ask you to find this derivative using the limit of the difference quotient, you have to use this. So you should memorize this. You can't just take the derivative using shortcut rules, even if you already know them. I know some of you might already have seen them before. So in trying to evaluate this limit, this f of x plus h is the first thing I need to think about. F of x plus h means in your f of x function, replace all the x's with x plus h. So I'll do that on the side, and then I'll substitute it into this formula. So f of x plus h is equal to, substituting into our function, x plus h quantity squared. Make sure that you're subbing in for x. The whole thing you're subbing in is x plus h, so it's x plus h that quantity squared, plus 2 times x plus h plus 1. Now, you could simplify this by substituting in there and then simplifying. I kind of like to do it in advance just so it's easier when I go to substitute it into the formula. So x plus h, the quantity squared, you're foiling this, right? It's x plus h times x plus h, which would give you x squared plus 2xh plus h squared. You're going to distribute this 2 through, so plus 2x plus 2h. Then you have plus 1. It doesn't look like any of those are like terms, so we can substitute this in all for the f of x plus h. So this equals, make sure you still write the limit in front, right? So you'll have the limit as h approaches 0. You need that. F of x plus h, now I'm replacing it with what I just found here, right? So the x squared plus 2xh plus h squared plus 2x plus 2h plus 1. And then I've got this minus f of x. Well, minus f of x is minus whatever f of x was, the original function, which is up here, right? X squared plus 2x plus 1. So we're going to say minus. And then make sure you put parentheses around this because this negative belongs to everything that comes after it. So all the terms. So minus and then the parentheses x squared plus 2x plus 1. That's subbing in for f of x. And then this whole thing is all over h. And so I want to simplify this. I'll distribute the negative sign through and then I'll combine like terms. So I'll end up with the limit as h approaches 0 of this, so let's write as x squared plus 2xh plus h squared plus 2x plus 2h plus 1. And then distributing the negative through, we'll have minus x squared minus 2x and minus 1, right? Negative times a positive makes each of those negative. Watch your signs there. This is all over h. And now you want to combine like terms, which really leads to a lot of canceling usually when you do this. We have x squared and a negative x squared, those will cancel. 2xh doesn't cancel. H squared, nothing to combine that with. 2x and a minus 2x, those combine and cancel. 1 minus 1, those cancel. And then this 2h doesn't combine with any of those, so I'm left with this limit. I have the limit as h approaches 0 of 2xh plus h squared plus 2h all over h. Now remember, you can't just sub 0 into this, right, when you're trying to take this limit. because that would cause it to be undefined. Here you can't just sub-zero in because, again, you still get something that's undefined. So what I really want to do is, once you're at this point, you should have all your terms with a factor of h in there. You want to factor it out. Because if you factor it out, then you're allowed to cancel. You can't just start canceling h's right now. All right, so make sure you watch out for that. You have to have a product, things being multiplied together in the numerator before you can cancel out those h's. So limit as h approaches 0 of factoring out an h from the numerator, I end up with 2x plus h plus 2. And this is all over h. And now I can cancel out these h's because now I have h times something. So I have multiplication, then I can cancel it with the same factor when I'm dividing. So I'm left with, and we're allowed to do this because, make sure you recognize, because h doesn't equal 0, right? We're talking about what happens as h approaches 0. And then we end up with, this is the limit as h approaches 0 of 2x plus h plus 2. And now that substituting 0 in doesn't cause a problem anymore, right, because it was being undefined when we did before, this 0 is now in the domain of this function. So I can substitute in and end up with, this is 2x plus 0 plus 2, which really just gives us 2x plus 2. So I did all of this to find what? Remember what we're trying to find, the derivative, f prime of x. So we know that f prime of x equals 2x plus 2. Alright, so f prime of x equals 2x plus 2, what we just found. So that was part A, find f prime of x. So a lot of times they might just ask you to find f prime of x. Remember, we said this is the slope of the tangent line. So once you know this is the slope of the tangent line at any point x for this function f of x that we have up here. I could actually ask you to find the equation of the tangent line at a specific point. Remember, tangent line is a line that hits the curve at one point, just touches the curve. So part B of this, let's talk about finding the equation of the tangent line. So part B, we'll say find the equation of the tangent line to f of x at x equals, and I'll say at x equals 3. So I have to tell you at a specific point to find the equation of the tangent line. So f prime of x, remember, gives you the slope of the tangent line. And when you're doing this, you know, to find the equation of any line, you need two things. You need the slope, right, and you need the point. So for the slope, that's where you're going to use the derivative, f prime of x. So f prime of x, we just talked about, f prime of x is equal to 2x plus 2, but we want the slope at x equals 3. Well, the slope at x equals 3 means I really want f prime of 3. F prime of 3 means you sub 3 in over c and x, so it's 2 times 3 plus 2. So 2 times 3 is 6 plus 2, this will give me 8. So what I'm really saying here is that, right, the slope you're going to use, right, this is the slope of the tangent line at x equals 3, because the derivative gives you the slope of the tangent line at any point x for the function. So you need the slope, you also need the point. To find a point that's on your function, right, so this point comes from the original function, you're using f of x, right? So f of x, just as a refresher, was equal to x squared plus 2x plus 1. We want the point when x equals 3. Now sometimes they'll give you the y coordinate with it. If they already told you at 3 comma whatever, you would just have to use the x value to find the slope. Because this just says that x equals 3, I need to find the y value. To find the y value, all I'm doing is substituting in 3 to get the y value, so we end up with 3 squared plus 2 times 3 plus 1. 3 squared is 9 plus 2 times 3 is 6, so 9 plus 6 plus 1, that gives us 16. So the point x comma y is 3 comma 16. So this is the point. Right? So your slope comes from substituting the x value into the derivative. The point comes from subbing the x value into the original problem, the original function, because that's what where the point lies on that curve. So remember, I asked you for what? The equation of the tangent line. And find the equation of the tangent line is just finding the equation of any other line. You need a point and you need the slope. We've got the point, we got the slope, and we can use the point-slope form. The point-slope form, remember, is y minus y1 equals m times x minus x1. And then you substitute in for the pieces you know. So we end up with y and x, remember, stay y and x. So y minus, what's my y value? y1 is 16 equals m, which is my slope, 8 times x stays x minus x1, which is 3. Now this is the point-slope form. We typically want it in the slope-intercept form. So to do that, we solve this for y. I'll distribute the 8 through. I have y minus 16 equals 8x minus 24. And then we can add 16 to each side. Make sure you're combining it with its like term. I get y equals 8x minus 24 plus 16 is a negative 8. So this is the equation of the tangent line to the function f of x equals x squared plus 2x plus 1 at the point 3 comma 16, right, when x equals 3. So this is the equation line that touches the curve, just that one point. All right, let's take a look at another one here. When we do this, all right, you may want to pause the video after I state the question just so you can try it on your own. But it is the same process as we just talked about. So taking a look at this one. So for f of x equals 3x squared minus 5. Part A, I'll say find f prime of x using the limit of the difference quotient. And like I said, you may want to pause the video, try it out, and then from there look at what we did when I work over it together. So, first thing you need is the limit of the difference quotient. Make sure you understand that f prime of x equals the limit as h approaches 0. Make sure that limit notation in there of f of x plus h minus f of x all over h. If the function had a different name, like g, you'd call this g of x plus h minus g of x, but it's the same idea, and this would be called g prime of x. And now we're ready to, substitute into our formula. The first part, the f of x plus h, I like to do that on the side. You don't have to, you could do it within the problem, but make sure you understand what it means. F of x plus h means you're subbing x plus h, and everybody's seeing x in my original function. In this case, there's only one spot to substitute it in for. The previous ones we had, multiple x's. Make sure you sub it in for all of the x values that appear. In this case, there's only one. So this would be 3 times x plus h quantity squared minus 5. Make sure you have an understanding of how this works. When I say x plus h quantity squared, you can't distribute 3 into this. You have to actually take care of the squared first. So this is actually equal to 3 times x plus h quantity squared. Remember, you're actually foiling this. It's not just square the x and square the h. You actually have to, multiply through binomial times a binomial. We've done this a few times over now, so I'm just going to write it. X squared plus 2xh plus h squared. But make sure you understand how to multiply that out. It's x plus h times x plus h. And then minus 5 is just at the end. This is equal to, distributing the 3 in, I have 3x squared plus, this will be 6xh, and this will be plus 3h squared minus 5. And that's how we're going to replace f of x plus h in this limit. So, I do this on the side just so I have it. So this limit, alright, so this is equal to the limit as h approaches 0. And you should be writing that limit notation in front of it until you've actually evaluated the limit. So we replace f of x plus h with this here, 3x squared plus 6xh plus 3h squared minus 5. And then remember, for this minus f of x part, it'll be minus whatever f of x was, that's the function 3x squared minus 5. Make sure you put parentheses around it because that negative belongs to all the terms in whatever f of x is. And then this whole thing is over h. To simplify this, I'll distribute the negative sign through. So it's equal to the limit as h approaches 0. You need that part. 3x squared plus 6xh plus 3h squared minus 5. And then negative times a positive makes this a negative 3x squared, and negative times a negative 5 makes this a positive 5. It's really like distributing a negative 1, remember. And then this is all over h. Once you've done it, we're going to simplify here. The 3x squared and the minus 3x squared will cancel. The negative 5 plus 5 will cancel out. These don't combine, they're not like terms. So this is equal to the limit as h approaches 0. We have 6xh plus 3h squared all over h. Make sure you keep that limit notation in there. Remember, you need it the whole way through. Alright, so make sure you're writing limit notation all the way through this until you evaluate it. You can't just cancel h's here. Remember what we have to do. We have to factor h from the numerator. So we have the limit as h approaches 0 of h times 6x plus 3h. This is all over h. And then now that we have a product, we have things that are being multiplied here, right? That factor now can cancel with the factor of h from the denominator, because we know h doesn't equal 0, right? H is approaching 0, but it doesn't equal 0. So we take this limit, right? The limit as h approaches 0 of 6x plus 3h. Well, now, since substituting 0 in doesn't cause us a problem from being undefined, we can sub 0 in right away, and we end up with 6x plus 3 times 0. Right now we've evaluated our limit. This is 6x plus 0, which is just 6x. So our solution, right, to f prime of x, right, what we found is that f prime of x is equal to 6x. So f prime of x is the derivative of f of x. So 6x is the derivative of 3x squared minus 5. Remember, if I ask you to do this using the limit of the difference quotient, you have to. Later on, we'll talk about some shortcut rules to get there. And then I'll just ask a follow-up about, remember, the derivative represents the slope of the tangent line, right? It's the slope for any value of x for the function f of x for the tangent line. So if I asked you to find the equation of the tangent line to f of x at the point -1, -2. So this is a little different than how I asked it in the last example, but the key here is that they're telling you an x and a y value. So I already know the point. Now when I say x is -1 and y is -2, it's really coming from this function, right? In f of x, when x equals -1, -1 squared would be a +1, 3 times 1 would be 3, 3 minus 5 gives you -2 for the y value. So all they did is they did the part where you have to find the point yourself for you, all right? So they already told you what the point was. But you still need what? You need the slope and the point. So we have the point, but we don't have the slope. So the slope, remember how you find it. The slope comes from f prime of x, the derivative, right? So f prime of what value do I want? Well, x that I'm looking at is -1. So you really want f prime of -1. So this will be 6 times -1, which just equals -6. So this is the slope, right? The point they gave us, right? We know what the point is. The point that we're looking at is -1, -2. If they didn't give this to you and they only gave you the x value, remember you sub the x value into the original function to get this y value. Right, so the slope comes from the derivative, the point that you use comes from the original. And then we're going to use our point slope form, right? The y minus y1 equals m times x minus x1, because we're looking for the equation of the line, so not just the slope, you're looking for the equation of the line. Substituting into this, we have y minus, the y1 is a -2, equals m, which is -6 times x, stays x, remember, minus the x1, which is -1. Watch your signs there. A negative negative makes these positives, right? So this would be y plus 2 equals negative 6 times x plus 1. And then we distribute in. So we got y plus 2 equals negative 6x minus 6. And then I will subtract 2 from each side. So I end up with y equals negative 6x plus, or minus, sorry. So y equals negative 6x minus 8. So that's using the limit of the difference quotient to find the derivative. The derivative gives you the slope of the tangent line at a point on the function f of x. Remember that when we talk about the slope of the tangent line, right? The tangent line is the line that intersects the graph only at one point, right? It just touches the graph at that single point. So it's important to know what we're asking you to do when you find the tangent lines. The last thing we want to talk about in this section is being what makes something differentiable, or what prevents something from being differentiable, really. So we're talking about being differentiable at a point. When I do this, these are things to look out for as we move forward talking about derivatives, because really that's what the rest of this section will be on. But we're going to talk about shortcut rules to get there. So the last part is just talking about what would cause something to be not differentiable. Why would there not be a derivative at a point? So I'll say no, a function is not differentiable at a point x equals a. So it could be differentiable at other points, but at a very specific point it might not be, right? So it's differentiable other places, but not at x equals a if it has and there's a few different conditions. So one way is if it has a sharp corner so it has a sharp corner or cusp at that point. And let me draw a little sketch of what that would look like. So if it has a sharp corner, so here's a, all right, this is an x and y axis. Suppose my function was like an absolute value, like a v type shape. At that point, x equals a, right, this function would not be differentiable. And mainly, that's because the limit come from one side would not be equal to the limit come from the other side. Right, the slope of this line as you get closer to this side, right, is actually going to be like a negative. The slope from this side would be a positive. Those slopes are not going to the same value. The limits are not going to the same value from each side. So that's what I mean by a sharp corner, or a cusp would be something like, as an x and y axis, here's our point A. If you had something like a curve on one side and then something pointy on the other side. And again, it's because the slopes wouldn't be equal coming from both directions. Or I should say the limits wouldn't be equal coming from both directions, which kind of shows you that the slopes wouldn't be the same. So if you have a sharp corner or cusp, not differentiable, right? Make sure you recognize that we're talking about when it's not differentiable, meaning it doesn't have a derivative at those points. The other points on these graphs would have would be differentiable, right? They would have derivatives because they're smooth in those areas. Remember, we're talking about this locally as you approach a point. Another way that it's not differentiable is if it has a vertical tangent line. At x equals a. Alright, so it's not differentiable if it has a vertical tangent line at x equals a. Mainly, if you think about what's happening here, right? Here's x and y. Vertical tangent line means tangent line that'd be going straight up and down, right? So if the function looked like this, and then here's the point A, we're saying that the tangent line that would hit this point would be going up through there. Vertical tangent line would be, something that has an undefined slope. So the derivative can't exist there if the slope is undefined. And the last way that it's not differentiable at a point is if it has a point, if it has a discontinuity. When I say discontinuity, I mean it's not continuous at x equals a. So in other words, it won't be differentiable if there's a jump, break, or hole in your graph. So the derivative won't exist. Here's x and y, let's call this a. If you said maybe, I'll draw it in red like I did the other ones. Alright, there's a hole there. So not differentiable if there's a hole at that value, because the function doesn't exist at that value, right? But even if there's a jump, or a break, right? Here's x, here's y, here's the value of a. You could have something like that, right? This is not continuous at a. It doesn't have a derivative there. Mainly again because the limit as you approach one side will not be equal to the limit as you approach the other side, right? So that's showing you that this will not be differentiable at the point at x equals a. Even though the function exists there, it's not differentiable because remember we're talking about this limit locally from both sides, and as you approach from the left side, it is different. So these are the ways that a function would be not differentiable at a point. It's differentiable in other areas, but at that specific point it isn't. So if it has a sharp corner or cusp, it has a vertical tangent line, or if it has a discontinuity, right? It's not continuous at the value of x equals a. As we get into the next sections, we'll talk about some shortcut rules to finding the derivatives.